All right, welcome to today's physics video. We're going to be learning today about inclined planes, all right? And really the targets today are pretty straightforward. You should be able to solve any of the problems that we had done previously on horizontal surfaces. You should be able to now solve those on a surface that is inclined, in other words, not horizontal, okay? So inclined plane is basically a fancy word for a ramp. All right, so we're going to start out here with a relatively straightforward example. So we've got a 40 kilogram box, and in the example it's placed on a frictionless plane. So we're going to start frictionless here to keep things simple, and it's inclined at 30 degrees, okay? Now usually the problem will say 30 degrees above the horizontal, okay? But if not, you can always assume that the angle that a plane is inclined at is measured off of the horizontal. So in this problem, here's my 30 degrees, okay? All right, so our goal is to find the acceleration. All right, so here's the problem. Up until now, all of the problems that we've done have had a horizontal surface, right? So you've got your box, and so the idea is, as we solve these problems, we think about our axes, right? And so you've got an x-axis and a y-axis, right? And the idea is pretty much all of our forces lie along one of those two axes, the x and y axes. You know, occasionally you'll have one of the lawnmower problems like we had in the last video where the force comes in at some weird angle, right? And then what you do is you take that force that's exerted at some weird angle and you divide that force up into components. One force that lies along the y-axis and one force that lies along the x-axis, right? And so, in essence, what we're doing is we're taking this force that doesn't lie along our coordinate system, and we're splitting it up into two separate forces that do individually lie along our coordinate systems. Okay? So, and then, you know, that everything works out because then our object moves horizontally, or not, or whatever. But if it moves, it's going to move along one of our axes, right? Okay? So, the problem here is when you put something on an inclined plane, 99% of the time, if the object moves, it's going to move either down the ramp or up the ramp, right? Okay? So for a problem like this, it doesn't make sense to use our traditional x and y axes, right? Because the motion then will not be along one of our axes, okay? And so that makes things a little bit more complicated. All right, so here's the deal. When you're solving a problem with an inclined plane, and only when you're solving a problem with an inclined plane, what we do is we abandon our usual coordinate system of, you know, x and y axes, and we replace those with two new axes with new names. All right? So what we're going to do now is we're going to use one axis that runs parallel to the ramp, okay? And we're going to call that the parallel axis. All right? And then the other axis is going to be an axis that runs perpendicular to the ramp, okay? So basically what we've done is we've taken our traditional plane that we call x and y, and we've kind of taken that whole thing and rotated it, and then renamed our two axes, okay? So that what used to be our quote-unquote x-axis, we now call the parallel axis because that axis is now parallel to the ramp. And the one that we used to call our y-axis, we now call our perpendicular axis because it is now perpendicular to the axis. All right? And so what this does is it makes it a little bit easier. A, because now all of our motion is going to be along the parallel axis. Secondly, because usually if somebody's going to, well, I guess, so that's one reason. Secondly, if there is friction, remember, friction is going to resist the motion, right? So our friction forces are always going to lie along the parallel axis, okay, right? Like if the block is, for example, sliding down the ramp, then kinetic friction would go up the ramp, right? Okay? Secondly, you know, if somebody's trying to push the box up the ramp, you know, let's suppose Roy is here. So here's Roy. Hello. So there's Roy pushing the block. Presumably, he's going to push parallel to the ramp, right? So most of our forces and our motion are going to be along this parallel axis, okay? And so that's why we want to use these axes, all right? The biggest problem, and it's not really that big of a deal, but the biggest problem is stupid gravity, right? So let's do this. A minute ago, we talked about, well, I don't need to redo that. We just talked about the fact that if you've got a force at a weird angle, you find the components of that force along your x and your y axes, right? In a traditional like lawnmower problem on a horizontal surface, right? Okay. Well, here we've got an inclined surface with a parallel axis and a perpendicular axis. The problem is gravity. Gravity sort of doesn't know that the block is on an inclined plane, right? So gravity still does what it always does. It pulls stuff straight down, right? So let's put in our force of gravity. Every time you make a free body diagram, this is your first thing, right? You put in your force of gravity. Okay, so our force of gravity in this problem is m times ag. So the mass of this block is 40 kilograms. Acceleration of gravity is negative 9.8 meters a second squared. Multiply it out and you get negative 392 newtons. Okay? So but the problem is that this force here doesn't lie along either of my two axes, right? It doesn't lie along either my parallel or perpendicular axes. Okay? So in the same way that we usually take that force of the lawnmower, force on the lawnmower handle, and split it up into components, we're going to do the same thing here. Okay? So what we're going to do is we're going to take this force and we're going to write it as one component that goes, how do I want to draw this? I'm going to undo that. No, I got to leave it like that for our triangle to work. So there's one component of this that pushes the block sort of into the ramp. So this is like the component of my force of gravity, which is perpendicular to the ramp. All right, and then there's another component which is parallel to the ramp. Okay, so the idea is here is my right angle. Okay, now it turns out that this angle here is the same as this angle here. Okay, and so in this blue triangle that I've got on the screen here, the FG perpendicular, this component of gravity, which is perpendicular to the axis, is our adjacent side. So we're actually going to use cosine to find that. Okay? So to find the perpendicular side, you take FG and you multiply by the cosine of your angle. Okay? Where your angle is theta, and again, it's the same as this angle in here. Okay? All right? And then similarly, you can find your parallel component by using the sine. All right? Now, a lot of students think this is counterintuitive because a lot of students associate cosine with horizontal. But here, it's your sine that gives you the parallel component. Okay? So, I guess before we go any further, let's take a quick second and jot this down. Okay? So, anytime you've got, so here's a quick summary. Anytime you've got an object on an inclined plane, gravity is going to pull down, but that's not going to lie along either of your axes. So, your first step in your free body diagram is find your force of gravity. Your second step now, because you're on an inclined plane, is to find the two components. Okay? And here are the equations that you're always going to use. To find your FG parallel, it's always going to be FG times the sine of theta. And to find your FG perpendicular, it's always going to be FG times the cosine of theta. All right? Those, you might as well memorize those because every single time you have an inclined plane, you're going to use one of these two equations. All right? So, now what we're going to do is, well, let's clean up this drawing a little bit here. All right? Well, yeah. So let's clean up the drawing. All right. So now what we're going to do is, so starting this problem from scratch, what we would have done is we would have said, oh, I've got a 40 kilogram thing. So 40 kilograms. I don't know why I'm doing this again. So this gives you negative 392 newtons. So that would be your step one. Your step two would be to say, oh, but it's on an inclined plane. So I should calculate my FG parallel and my FG perpendicular. So FG parallel is FG times the sine of theta. So for me, that's 392 newtons, I guess negative, times the sine of 30 degrees. So if you solve that, you find out that your FG parallel is 196 newtons. Negative, as in it's going down the ramp. Okay? Similarly, I need to find my FG perpendicular. So that's FG times the cosine of theta, which is negative 392 newtons times the cosine of 30 degrees. And so I find that my FG perpendicular is, if you find it, it gives you negative 339.48 newtons. Okay? So, starting a problem from scratch. Oh, I've got a 40 kilogram thing. Find your force of gravity. Oh, it's on an inclined plane. Find these two components. Okay? Now I'm going to proceed with making my free body diagram. All right? So I'm going to clean up the board one last time. Do you know what though? Well, yeah. Yeah. Okay. So what I'm going to do is when I make my free body diagram, instead of drawing in my force of gravity, I'm going to draw in my components along my parallel and my perpendicular axes. Okay? So just a moment ago, I calculated those values. So the idea is there's a component of gravity that pulls the block down the ramp. We call that FG parallel. We just found that a minute ago. It's negative 196 newtons, right, down the ramp. All right? And then there's another component of gravity that pulls it into the ramp, FG perpendicular. We just found that, and it was negative 339.48 newtons. Okay? So that is our new step one. All right? And this seems like a drag, but from this point forward, you're going to do it so many times, I think it's going to really become second nature to you. All right? So again, the time when you need to do this is when you've got a thing on an inclined plane. All right? And to be clear, what these two blue vectors that I just drew represent is they represent the force of gravity. If I use vector addition and I add these two vectors together, I just get the force of gravity. Okay? So really quickly, just so you can see that, look, if I take this and put it over here, now vector addition, remember, place them head to tail, here's my force of gravity, right? Okay? Or alternatively, if you prefer, I could have taken this guy and moved, taken this guy and moved it down here and found my force of gravity. Okay? So all I've done is I've replaced my force of gravity with two components which lie along my axes. Okay? Now, next order of business. If the block moves, it's going to move along this parallel axis. The motion is going to be along that red line, right? And there's going to be no motion along this, oh shoot, that's not what I wanted to happen. There's going to be no motion along this perpendicular axis, right? There's no motion along there. Okay? So the idea is this this perpendicular component of gravity is pulling the block down into the ramp. But for some reason, the block doesn't move down into the ramp. Well, there's a normal force, right? Now remember, I don't know if this is a thing that we talked about, but it hasn't come up a ton recently. The normal force is always perpendicular to the surface. That's the word normal in math means perpendicular. Okay? So for the purposes of this class, okay, as in unless you take AP or go farther in your physics education, for the purposes of this class, anytime you're on an inclined plane, you can pretty much flat out assume that your normal force will exactly be canceled by this FG parallel. So my normal force here is just going to be 339.48 newtons. Okay? So those are going to always cancel. Really, the only reason that we need to calculate this is because it's going to be important for problems where there's friction. Okay? So, I think that's it. I think those are the only two forces. Well, I say two forces. The only three forces acting on this, right? The two components of gravity, which is really one force, and the normal force. Nobody's touching it. It tells you it's a frictionless plane, so that's it. Okay? So, our net force along the perpendicular axis is just 0, right? Because, shoot, I don't have enough colors. Because this force and this force cancel each other out, so our net force vertically is 0. All right? What we're really concerned about is the force along the parallel axis, which is this, right? And so, what that tells us then is our net force is really just the net force along the parallel axis. That's probably more notation than you needed to use. So, let's see. Our net force here is, oh, well, it's just Fg parallel, right? Which is negative 196 newtons. Oh, so now I can find my acceleration. Acceleration is net force over mass, negative 196 newtons, divided by 40 kilograms. Divide this out, and you get negative 4.9 meters per second squared. All right, well, your free body diagram would look like what's on the screen right now, but without the red, okay? And then your acceleration we just found, right? It's 4.9, okay? So, I guess kind of the way that you want to think of this is you're sort of in this like tilted reality where your gravity and your normal force are going to always cancel. Sorry, let me say that differently. The perpendicular component of your gravity and your normal force always cancel. All right, and then you've got this other mysterious parallel component of gravity, which is always pulling the block down the ramp, okay? Now, in a minute, we're going to deal with friction. Remember, friction resists motion, not force, okay? With these inclined plane problems, we're going to always have a force pulling down the ramp, right? This parallel component of gravity. But you won't always have motion down the ramp. Sometimes you'll be pushing it up the ramp, right? Okay. So let's try another problem. All right. So I'm going to do this one as I would expect you to do a problem for a homework assignment. All right. So here we go. So a 30-kilogram box is sliding at 6.5 meters a second when it begins going up a ramp inclined at 25 degrees. So I'm going to start by drawing this. Here's my plane. I know it's inclined at 25 degrees. Here's the block. It's got a mass of 30 kilograms. I know that it's got an initial velocity of 6.5 meters a second up the ramp. And I know that my coefficient of static friction is 0.5, and my coefficient of kinetic friction is 0.4. Okay? So the question is, how far will the block or the box slide up the ramp before stopping? All right, so I've written down all my given information. Step 1, force of gravity. So Fg equals mag. So 30 times 9.8, you get, let me write it out, 30 times negative 9.8, so you get negative 294 newtons. All right, now, I'm not going to put this on my drawing yet, okay, because I recognize, oh, this thing is on an inclined plane. So it's not really the force of gravity that I care about, it's the two components, right? So let's do this. Oops. Okay, so let's do this. Let's take a second and go off to the side over here and find our two components. So our Fg parallel is, well, that's always Fg times the sine of theta. So for us, it's negative 294 newtons times the sine of 25 degrees. Okay, so if you grab a calculator or machine and figure out that answer, it gives you negative 124.25 newtons. All right, I'm hanging on to some extra significant digits here. All right, similarly, we can find our Fg perpendicular. So that's Fg times the cosine of theta. All right, so that's negative 294 newtons times the sine, times the cosine of 25 degrees. So that gives us negative 266.45 newtons. All right, so that's my step 1. Find the force of gravity, and because it's on an inclined plane, find the components. All right, so now I'm going to take those numbers and I'm going to put them over here on my drawing. All right, so let's see, we just found Fg parallel. That's the component that goes down the ramp. I don't know if I've said this yet. That parallel component, this one that I just drew, always goes down the ramp, right? Because gravity always wants the block to go downhill. That's what gravity does, pulls stuff down-ish, right? Okay, so, okay, so here we go. So we've got a ramp. Sorry, my board was just getting cluttered. All right, so we had decided that this thing was, what, 30 kilograms, and we just found our components. All right, so FG parallel, that's this guy, negative 124.25 newtons. All right, and then there's also a perpendicular component that always points into the ramp. Always points into the ramp. So that's negative 266.45 newtons. And then finally, I know that the block is not actually going to go into the ramp, so I can automatically put in my normal force, which will be positive 266.45 newtons. Okay, so there's my drawing so far. All right, now, the next thing we need to deal with is this. It started out moving up the hill at 6.5 meters a second, right? The problem tells us that here. It's sliding at 6.5 meters a second when it starts going up the ramp. Okay, so what that means is, since it's going up the hill, there's going to be friction pulling it down the hill, right? What kind of friction? Well, it's sliding, so there's going to be kinetic friction, right? And notice, since the velocity is up the hill, my friction is going to be down the hill. All right, so somewhere off to the side, I got to calculate my force of friction. All right, so my force of friction kinetic is, oh, well, that's my coefficient of kinetic friction times my normal force. And the coefficient of kinetic friction here was given to be 0.4, sorry, right? Wasn't it 0.4? Yes, 0.4 times our normal force, which is over here, 266. So multiply this out and find that your force of kinetic friction is 106.58 newtons down the hill. So I got to make it negative on my drawing. Okay. So I think that's it. It doesn't tell us anything about there being a force pushing it up the hill. So I think we're done now. So now what I can do, oh darn it. There we go. Now what I can do is I can say, oh, well, my net force is the sum of all my forces. So the two green forces cancel out. So I'm just left with FG parallel and the force of friction kinetic, which is negative 124.25 plus negative 106.58. So my net force here is going to end up being negative 230.8 newtons. Is that right? I guess 0.83 newtons. So I can find my acceleration. Divided by the mass, which was 30 kilograms. And I get an acceleration of negative 7.69 meters per second squared. All right? And the problem wanted to know how far it would slide up the ramp before it stopped. So, oh my gosh. There we go. So, let's see. Here's what we know. We know our initial velocity is 6.5 meters a second. It's going to stop eventually. We just found our acceleration. We want to know how far it's going to go. So dig out your old kinematics equations, and I think that this guy will work and solve for displacement. All right, I'll leave you guys to do the algebra. If you solve this, you get 2.745 meters. Okay, so that's how far the block slides up the ramp before it stops. All right, so that is part A. Okay, now part B. Part B says, will it slide back down? If so, how long will it take to slide back down? If not, how much force would I need to make it slide back down? Okay, so we need to make a new drawing here because right now our box is stopped and we need to figure out what's going to happen. Okay, so here is our ramp again. All right, we've already found our FG perpendicular and our Fn, those were negative 266.45 and positive 266.45. We've got our FG parallel, which is negative 124.25, all right? And right now, our box is at rest. It's just stopped, and our new problem begins with an initial velocity of 0, all right? So it's going to try to slide down the ramp. Why? Oh, well, because gravity is pulling it down the ramp. So the question we want to ask now is, will it move? And to answer that, we have to decide, can static friction prevent the motion? All right. Well, to find out if static friction can prevent the motion, we got to find our maximum static friction. So that is our coefficient of static friction times our normal force. So the coefficient of static friction was 0.5. Our normal force was 266.45. So multiply this and you get 133.23 newtons. So that's how much static friction we've got. All right. So let's think about what's happening here. So what we just decided is this. Static friction has 133 newtons worth of force in its wallet, right? I don't know why I'm highlighting this so carefully, but now I've missed it. There we go. Okay, so that's how much force friction has in its wallet, right? And meanwhile, gravity's pulling down with this much force. So can static friction prevent the motion? 100% it can, right? Because to prevent the motion, you would just have static friction going up the hill with a force of 124.25 newtons, and you'd be done, right? You know, I don't think I need to finish this example for this to all make sense. I think I've hit the important stuff. All right, so I'm going to stop there.